This video presentation is our team project summary for the design and fabrication of microsystem course. We are team 4, Ryuko, Kwon Chung, and Iritiza Muhammad Sakib. In this presentation, I will explain the pressure sensor design and fabrication process using semiconductor process. This includes the detailed step and technical method we will use. Then performance evaluation with wired and wireless system will be discussed, as well as the project schedule and individual contribution. A piezoresistive pressure sensor is a device that converts pressure into an electrical signal using a piezoresistive effect. The key feature of pressure sensor include high sensitivity, a wide range of applications, and the ability to integrate with semiconductor technologies. When pressure is applied, a diaphragm undergoes deformation, which leads to change of electrical resistance. Using this Whiston bridge, we can detect these resistance change and convert them into a corresponding voltage output. So when we can measure, amplify this voltage and current signal from the circuit, which corresponding the applied pressure. In order to design the sensor, we need to determine the overall size of the design and thickness of each layer and the pattern of the sensor. We can confirm this parameter using the finite element method we call the FEM to check the diaphragm deflection. We are considering to use the COMSOL or CATIA as a simulation program. Based on the FEM simulation result, we can calculate the theoretical displacement and resistance changes and corresponding output voltage of the sensor. Since the design will highly affect on sensor sensitivity and linearity, so we will be more carefully designed. Once we determine the structure from the simulation, our next step is to design the mask. We will use 2D drawing software such as AutoCAD to design the mask pattern. For the pressure sensor, we need to design and prepare 3 kinds of masks. First, the air window pattern. This is used to control the thickness of the film. The second pattern is to make a Whiston bridge circuit, and the last pattern is to etch silicon from the backside and make a cavity. Next, I will move on to the detailed semiconductor fabrication process. First up is the silicon wafer preparation and cleaning process. We are going to use a 4-inch silicon wafer, and the cleaning is most important. Piranha cleaning. This is the first step which removes organic contamination from the surface. Next, we will do RCA1 cleaning to get rid of any remaining particles and impurity. Then we will do RCA2 cleaning, which removes any metallic ions. A cleaning silicon wafer is necessary for precise semiconductor fabrication. Next is the first summer oxidation process. We will use this furnace to deposit the 3 nanometer layer of silicon dioxide on the silicon wafer. So after that, on this blue silicon wafer, get this green silicon dioxide layer. After that, we will carry on the photolithography for the silicon dioxide etching process. First, we will coat the silicon wafer with photoresist AZ5214 using this kind of spin coater. Then this orange color photoresist will be coated as shown in this figure. After exposing the UV, the pattern will be created like this way. So once we get the pattern, we will check the pattern using the microscope and SEM to ensure the quality of the patterns. Next step is open window pattern etching. We coat another layer of photoresist on the backside of the silicon wafer, and this layer acts like protective buffer during the BHF etching process, and then remove the silicon dioxide in BHF solution. And TMAH etching will be conducted to control the thickness of the silicon. So we will use a furnace to deposit silicon dioxide layer about 500 nanometer on the silicon wafer, and this will protect the silicon from the damage by TMAH solution during the etching process. To isolate the metal strain gauge from electrical substrate, insulating layer need to deposit. So you use AG5214 to make a sensor pattern by photolithography method. And after developing the pattern, the sputter system will be deposit a 100 nanometer layer of chrome onto the wafer so that this metallic layer will be deposited, and the lift-off process is required to remove the unnecessary chrome, leaving behind the desired sensor pattern. Last step is backside etching. Firstly, we create the pattern using photolithography and apply the photoresistive layer on the top side. Before silicon etching, we need to remove the silicon oxides with a BHF solution. Then we can etch the backside silicon with TMAH for approximately 20 hours until the undesired silicon pattern is completely removed. After that, the sensor needs to be packaged to protect its component to apply the pressure to the sensor. We will assemble the final device using 3D printed jig to secure all the components. And we will connect the wire with conductive epoxy for proper electrical connections. Additionally, we will create the channel for pressure application using an injection device. And wires are bonded at the metal contact pad, which can connect to the external lead-out system. Once the assembly is complete, we will evaluate the sensor performance using wired and wireless system. When pressure is applied, the 4 resistor will changes at the piston bridge, and the bridge generate different output voltage that is corresponding the applied pressure. But however, the voltage is really small, usually in the microvolt. So we will select the proper amplifier, such as an OP amp, and connect it into the piston bridge in the device. So our pressure sensor will connect with OP amp. I will call it as HX771, and this signal is measured from the Arduino system. And signal will be input in the Arduino analog input pin and transfer into the digital output so that we can get the amplified sensor signal. So each sensor signal and the required power is connected at this port. And to make this system wireless, we can use the RF device, especially an RF24L01. So this will be sufficient to remotely transmit and receive the data from the Arduino. And based on the obtained voltage data, we can evaluate the performance of the sensor. So after applying air pressure, we can measure the sensor signal, and if we can measure the actual pressure, we can calibrate our sensor. Additionally, we discuss about the another method to implement the wired system. Using the AQ board and LabVIEW system, we can also set up the wired system. But I think we need to further discussion is required to check if this board can be used or not. And using the low data, we can find the relationship for the calibration. And we will develop the program to receive the data and transmit the signal and visualize the result. The performance of the sensor will be evaluated from various aspects, including sensitivity, linearity, hysteresis, repeatability, and signal-to-noise ratio, and so on. This is our team project schedule to enhance the efficiency of the fabrication process and the performance evaluation. We may divide the task, so we design and fabrication together. At the same time, the wired and wireless system will be implemented in advance so that it can be evaluated together. Lyrical will mainly focusing on design of the structure and mask pattern, fabrication of diaphragm and pressure sensor, and performance evaluation using wired system. And we will discuss together on sensor structure analysis with a PM simulation and implement the wireless system. Cohen will mainly focusing on implementation of wired and wireless system and evaluate the sensor's performance and design and manufacture of assembly components and theoretically calculate the analysis of piston bridge. Additionally, same as Lyrical, we will discuss together about the sensor design and participate in the entire semiconductor fabrication process and decode our process. And Iritiza will mainly focusing on sensor design and simulation process and fabrication process, including wafer cleaning for photolithography process and evaluate the sensor evaluation. So this is all our presentation. Thank you.